Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to the 33rd lecture of VLSI Interconnects course. We are currently in the 4th module and we are discussing coupling in interconnects. In the previous lecture, we saw the matrix formulation for coupled RLC interconnects. We saw that even for inductive interconnects, if they are identical, common mode and differential mode analysis is valid. In this case also for RLC interconnects, we again saw that the decoupling was equivalent to diagonalization of your matrix. And then towards the end we saw an expression for frequency domain crosstalk noise. However, in general interconnects are not identical and also there are large number of interconnects. So, in that case our common mode and differential mode analysis will fail, and in that case we have to rely on this highlighted thing, decoupling is equivalent to diagonalization. So, in this lecture we will look at the method of decoupling the interconnects by basically diagonalization of matrix. So, let us get started. So, as we have seen that your decoupling of equations was equivalent to the diagonalization of your matrix. So, whatever be your system of coupled equations, you can have either an RC or you can have RLC interconnects where there would be a term of LC and RC like this. And then for this, if you are assuming time harmonic voltages, then as we had discussed in previous lecture, that your del by del T would be replaced by j omega, and then finally you will be getting this. So, here if there are n coupled interconnects, then you will have n cross 1 voltages here, this will be your n cross n, this will be your n cross n. So, basically this we can represent as gamma, and you can have an equation of this form which you want to then decouple. So, here in general what will happen is that you will have some diagonal terms and then you will have some off diagonal terms. Not all of them would be non-zero. So, depending on how you are coupling, you will have other terms. Some terms will be 0, some terms will be non-zero. But in general there will be in system of coupled interconnects, there will be these off diagonal terms. So, these if you look at it, these off diagonal terms are responsible for coupling. So, there will be for example, a voltage V1, V2 and so on going up till Vn, and then if you want to find what is the dependence on this first term, the double derivative of V1 depending on this. So, first term will be like straightforward. So, this term into V1 plus this off diagonal term plus V2. So, this off diagonal term will contribute to your to include this V2 in your V1. So, these off diagonal terms are the main issue which we want to handle, right. So, to decouple these equations, what we do is we transform your V to V tilde in general, and this transformation should be such that after this transformation you should get the differential equation like this, where this now becomes a diagonal matrix. So, your transformation should be V tilde is equal to T into V, and once you do this transformation, basically you would substitute V in terms of V tilde in this equation. For two identical RC interconnects, we did that process, and finally this should be diagonal. So, if this is diagonal, then there will not be any coupling. So, if you have something like V1 tilde, V2 tilde, so on. Now, I am not writing V common mode or differential mode, because those definitions does not hold any meaning now. And then you will have a matrix like this, and then this will be multiplied by, okay, let me this will be multiplied by there will be a D2 term here. So, V1 tilde, V2 tilde going on till Vn tilde, and here now you will have only the diagonal terms, right, and all other terms would be 0. If you have this, then you would have a system of decoupled equations which can be solved. So, our problem is then basically diagonalizing the matrix, this matrix, which would I mean, we will see, like, which would hold this transformation. So, there are many methods of diagonalization. There is LDU diagonalization, but that will not help us. So, we will see. So, in general, let us say that we want to diagonalize a matrix A. This can might be covered in many of your previous courses, but for completeness we will look at this diagonalization process again, and then see what it means for interconnects. So, now depending on your differential equations, we want to decouple A, right. So, A can be depending on what is the equation you are solving. So, A can be either your RC matrix, or it can simply be your LC matrix, or it can be your gamma matrix, or it can also be your transfer function matrix, right. So, from experiments, experimental results, you can you might possibly simulate or measure the scattering parameters. From that you can get the transfer function. So, if you have a large number of coupled interconnects, maybe you can do measurements and get the coupled transfer function between them, and from there also you can get this. So, our goal then is to diagonalize this. So, depending on scenario, so this would be R resistive and capacitive only. So, these two will be R, L and C. So, in this case there is only, say, LC, in this case there is R, L and C, right. So, let us make this a general problem. So, the task before us is the following: we have to find T such that we get V tilde, right, and V tilde, I mean, not any transformation, right. I mean, we can define this T, but what would be the constraints? The constraint is the following, that I am substituting my V. So, this will give me what? Let me write it lighter, yeah, this is visible. So, this V I can write as T inverse into V tilde. Now, if I substitute this V in any of this differential equation which it is governing, so basically I may have D2 T inverse into dx square is equal to some matrix A. A can be gamma, A can be RC, there would be a gamma square here, yeah. So, in this case you would have or let me write the final thing. So, this would be T inverse into V tilde, then there will be a V tilde term here. So, then you can bring it on this side, and finally, what you will be getting is a term like this. So, you will be having this is a T inverse. So, T A T inverse. So, this should be your diagonal. So, this is the constraint that we have, that you want to find a transformation T, transformation matrix T, such that this will give you a diagonal matrix D, right, and D should be of this form. So, lambda 1 to lambda n. So, all these are zeros, right, all off diagonal terms here terms are 0. So, now our final problem statement is following: given A, how do we get A? A we get from the differential equation that we want to decouple, and we get that from the interconnect. So, from the interconnect parameters, the individual interconnect parameters and the coupling coupling parameters like C and L and mutual coupling, we will get A. Given A is given to us, what is T and what is D, such that I am getting this, right. So, I can basically I am getting this, right. From this I can pre-multiply this equation by T inverse, and I can get this equation, right. So, I have this equation. Now, in this equation, this is a matrix and this is a matrix. So, we can go on handling this matrix as T inverse, but that will complicate the notation. So, just for that sake, let us call this T inverse as a new matrix P. So, this is for simplicity. So, simplicity of notation, basically I do not want to handle this T inverse throughout. So, let us call this T inverse as some matrix P. So, what I have is P matrix multiplied by D is equal to A into P matrix. Now, what should be the dimension of your T matrix and finally P? So, if you look at this, if there are n interconnects, the size of this would be n cross 1, the size of this should also be n cross 1. So, then if T multiplies with this to give you an n matrix, so this would be n cross n, right. So, T is n cross n, so then your T inverse is also n cross n and your P is also n cross n, and this is also n cross n, right. So, basically you then have to find out a matrix P that will satisfy this condition. Note that there is, as of now, there is no constraint on D. We do not know D, all we know is A. We do not know D, we do not know P. So, how should we proceed? So, let us represent P as a block matrix of its column vectors. So, P is a matrix, P is n cross n. What we will do? We will represent P as a block matrix, and this is like column vector. So, these are like individual values, and this is a column vector. So, there are n such column vectors, you can assemble them together to make your big matrix P. So, what I am saying is, let me explain again. So, I have a matrix P like this, the size is n cross n. I am having this and this, and these are like the columns. So, what I am doing is I am calling this column as alpha 1, this column as alpha 2, this column as alpha I, and this column as alpha n, and then I am assembling all of them together to get my P matrix as alpha 1, alpha 2, alpha I, somewhere in between, going all the way up to alpha n. So, then if I substitute this expression here, so let me number this as 2 and let me number this as say 1. So, I am just substituting now P in terms of alpha. So, I will get this equation, right. So, this is my D, this is my right. So, I have these columns. Now, if you look at the nature of this matrix multiplication, you can see that I can write this multiplication as a block matrix of these individual multiplications. So, A is now multiplied by this column vector, then A is multiplied by alpha 2 and so on, and then you can assemble them together to get the final equivalent thing, and you can check that how this comes. Then on the RHS there is this interesting thing happening. So, in the D matrix, what was the constraint? Off diagonal terms are 0. So, only the diagonal term is present. Now, if I look at this, how this would multiply. So, P11 would multiply with lambda 1 and all other terms then would be 0 in that addition, right. So, for the first thing you will get only lambda 1 into P11. Now, if you look at the first element of the second row, your P21 would be multiplied by again lambda 1 and then all other terms in that summation would be 0. So, your second term would be, I mean the second term means the second row first element, that would be lambda 1 into P21. So, you can then write this because of this diagonal nature, you can write this as simply this. So, lambda 1 into alpha 1, lambda 2 into alpha 2, lambda I into alpha I, lambda n into alpha n. Now, if this equality has to be true, then what it means is that, I mean, all the elements have to be equal. So, all the columns have to be equal. So, if I if I take say the ith column, so this should be equal. So, I can then finally write this equality in this form. So, A into alpha I is equal to lambda I into alpha I. Here I belongs to this range 1 to n. So, for all values of I going from 1 to n, this should be true. Now, interestingly, this might be familiar to you. This is what we have studied as eigenvalue equation. So, you might have studied this in your undergraduate maths. The problem now is reduced to the finding eigenvalues. So, what we have to do is we have to find the diagonal elements. So, basically diagonal elements of this, right, D is what? Lambda i's, right. So, you have to find the diagonal elements lambda i's which are the eigenvalues of the matrix A, and the column vectors alpha i's are the corresponding eigenvectors. So, this is your eigenvector, and this is your corresponding eigenvalue. So, basically what we have done is that we have reduced the problem of decoupling of equation to diagonalization of matrix, and then that is reduced to finding eigenvalues and eigenvectors. And with efficient algorithms, this finding eigenvalues and eigenvectors can be easily done on computers. So, just for completeness, let me also say give you like how do we find the eigen values. So, basically this equation has to be true. This would be true if this equation is holds, right. So, this equation holds. So, basically eigenvalues, and I mean non-trivial solution would be when the determinant of this goes to 0, right. So, eigenvalues are the roots of this equation, this is the determinant. This is the determinant of this matrix A minus lambda I. So, you put that determinant equal to 0, you solve the roots, you will get lambda i's, and this will give you, this equation will give you lambda i's. So, to start with you had the only information was this A. From A you can solve this equation and get the lambda i's. Once you get the lambda i's, you can then assemble them to form your diagonal matrix. You can find the eigenvectors and assemble them to get your transformation matrix. So, let me summarize the steps that are involved in analyzing these coupled interconnects. So, we start with determining the governing equations and the coupling matrix. So, finally, you will have A, and then A can be your RC or your LC or your gamma square, etc. Once you have got this A, you solve this equation, determinant of A minus lambda I equal to 0 to get values of lambda i's. Once you get these lambda i's, then you have to form this decoupled diagonal matrix, and that decoupled diagonal matrix would be given like this. So, if you have system of n coupled interconnects, you would get these n eigenvalues that will allow you to decouple these interconnects. And once you have this, then you compute the eigenvectors. So, for each of this you then compute what would be your eigenvectors. So, your A into alpha i's would be lambda I into alpha I. So, your lambda i's you have got from here. So, you have got this lambda i's. You know A, you have to get these eigenvectors. Then you arrange all those eigenvectors to basically give you P, right. So, your P is alpha 1, alpha I going up till alpha n, and note that this P is actually T inverse. So, then you have to invert this, you have to invert this to get T, right. Then from the transformed this transformation matrix, you get the transformed voltages V tilde S T into V, and from there you then solve it, and then after you have solved it, you then again decouple to T inverse yes. So, this gives you the final thing. So, these are the general steps which would be involved. You could implement these in computer code if you know A, right. Yeah, there would be a matrix here. Yeah. So, now in when I was discussing mitigation techniques, So, when we are discussing coupling mitigation techniques, there was one subcategory where the solution was sought in on the signaling level, right. So, there was this technique of signal level. Signal level mitigation. In that, I had towards the end I had shown you this reference. So, the title was optimal terminations for crosstalk mitigation of high speed interconnects with discontinuities using modal signaling. So, what we mean by modal signaling? Now, we are in a position to understand that. So, in that in this reference there was this figure, there was an encoder and there was a decoder, and these are like coupled interconnects. So, there are these coupled channels. So, now what we do is this what is this T? This T is what we have derived. This is the same T as we have derived in this lecture. So, if you look at this paper, it is a lot more detailed, lot more things are covered there than we can possibly cover in this lecture. But there you can see that there is this coupled matrix like this, and then here you can see there are this. So, this is your so earlier you had a coupled equation. So, equation 1 was a coupled equation. This equation is a decoupled equation where you have this form, right. This is your form of T and this is your T inverse. You can see this inverse, and then this is a diagonal matrix. Here you can see that there is a statement resulting submatrices of eigenvalues lambda. So, this we have seen. Resulting submatrix of eigenvalues lambda and eigenvectors W describe the forward and backward propagating waves. So, now after going through this lecture, it will be clear that why the eigenvalues and eigenvectors are coming in this. Here again, if you go into more detail, there is a statement like once the diagonalization has been performed in the frequency domain, the near end encoder T, the near end encoder, let me highlight it with a different ink. The near end encoder T for unidirectional signaling can be realized by imposing linear combinations of voltages as given by matrix element this, or by imposing linear combination of currents given by matrix like this. So, basically here this in this method what is happening is that all these bit streams are then combined to form different modes, and then different modes are being propagated, and at the other end you are again decoupling them. So, basically this is what is called the modal signaling. So, this is mode 1, mode 2, mode 3, and this is like, so there is this with optimal terminations and this is without optimal terminations. We also need to have an optimal termination here, otherwise there will be reflections and then it becomes a lot more complex. But here you can see that the crosstalk, the crosstalk induced jitters and all those things are then suppressed. So, this is one way of handling this mitigation technique, and for that you need to understand this. So, I will stop here. In this lecture we saw steps for diagonalizing a coupling matrix. We saw what is the general procedure. This procedure can be applied to RC as well as RLC interconnects, and this is scalable. So, this can be scaled to large number of interconnects. In the next couple of lectures, we will apply this process of diagonalization of coupling matrix by taking some examples. In the next lecture, we will be taking the case of 2 coupled interconnects, and in the next lecture, we will take the case of 3 coupled interconnects. So, that is all for today. I will stop here. We will meet in the next lecture. Good day.